don't see Peter on the call yet, Rob.
No, so we had some computer problems, which we saw. He was going to be in the room with me,
Right.
but he sorted himself out onto another computer, and he'll have to present his half of the talk there, if that's okay with you.
Just he'll need to ping me when he joins so I can give him sharing permission, because at the moment he wouldn't have sharing permission. I don't see him logged in at the moment.
No, he's off getting the quad to show you guys.
Right.
So he's down the end of the corridor collecting bits of quad. And
okay, all right.
Getting through a couple of security doors. So he should turn up in about 5 minutes or so.
Right.
Yeah.
No worries at all.
He'll be on Discord. So yeah.
Yes. All right. So I'd just like to introduce Professor Rob Mahoney from ANU, and he's presenting with Pieter van Goor on a new open visual odometry system that the lab at ANU has been developing, which is producing some exciting results. And so over to you, Rob.
Thank you very much. So I was enjoying the discussion about displaying the rads and the degrees actually earlier too, but this is my turn now, so I'll keep going. So look, we've been working away in this visual inertial odometry area for a few years now, and those of you that were here last year would have seen I gave a talk, and we got in the guy from the T265 to talk a little bit about that unit as well. So what I wanted to talk to you today about is really where we're up to in this, and we've actually got Pieter has been doing a lot of the heavy lifting in terms of doing the code and some experiments. We've got some really neat experiments that Tridge helped us run. We were flying last Sunday, and we got some data to show you from that shows you where we're up to, and then we'll talk a little bit from there. So this talk, I guess we're going to split it into sort of 3 bits, where I talk a little bit about the underlying motivation and how it fits into modern thinking in filtering. So there's a little bit of maths in there, but I'll try not to bore people with it. And then Pieter will talk a lot about some of the practical issues and give you a bit of an impression of where we're coming. So just to talk a little bit about what's the academic field sort of looks at in this space. So there's this whole sort of field of visual odometry or spatial awareness, and it sort of includes 3 topics, which are these 3 topics down here. And so it's an interesting thing from the academic community, right? There's a lot of focus on this first topic, on simultaneous localization and mapping. You might have heard about it. All of these 3 topics have a lot in common in terms of the mathematics. But it's really the third of those that's most interesting to the ArduPilot community. So the point about simultaneous localization mapping is it's a problem where you've got a robot and it's moving around in the world, and really what you want to do is, after the robot has flown through that world, you want to be able to rebuild a model of where you went. So it's that there was a group of people did it a few years ago, build Rome in a day, take photographs of Rome, figure out where all the cameras were, reconstruct 3D model of the whole of Rome. Well, they didn't quite do the whole of Rome, but they certainly did quite a lot. And when you've got a robot actually moving, it gives you a lot of construction. So the point about that is it's really not about knowing where the robot is, it's more about building a map. And so that's not really our focus for the ArduPilot community that we're working on at the moment. So then there's what I was really talking about last year, which is visual odometry. And the point about visual odometry is that you don't try and add the inertial measurement unit into it. You just try and use the pure camera to build a model of where you've been and where you're going in the world. And so that's a very interesting academic question. And interestingly enough, the actual mathematics of that problem is easier than the mathematics of the inertial odometry, which is the last one. But the practicality of it isn't there, right? Because if you do have an inertial unit, you should be using it, and you get much, much better results if you do. So from a point of view of actually putting a piece of software on a drone, you'll never be flying without an inertial unit. You couldn't anyway. So you should be using that data in what you're doing. And interestingly, that perspective that I was just talking about is some of the issues that we've been starting to tackle, where we've come in from the academic point of view with an algorithm. Now we're having to deal with multiple time domains on the the filter computer to the ArduPilot computer and remove time jitter and estimate time lags and all of the reality of actually making these systems work robustly in the real environment. So the problem that we're really interested in is this final one, which we call VIO, and that's where you've got an inertial measurement unit that you're getting the data from, and you've got other sensors potentially like barometers and magnetometers that we're going to be wanting to include, and then you've got access to a camera, and usually with the other requirement, access to a camera and enough processing power to do something with the images that you get in. And so this is the results that we got in our group, and hopefully this works. So this is an academic data set. So it's a data set that's generated by the University of Zurich in Switzerland, and it's called the UROC data set for anybody who knows these data sets. So it's a data set that was built and designed specifically to test these sort of algorithms, right? And so they took off inside a room, as you can see, and the quadrotor flies around. It does lots of turns. But what stands out in a data set like this is there's environment all around the drone all the time. You're never high up and looking down at the ground, which is actually a bit of a singular case for most visual inertial odometry systems. And the other thing for this data set is they give ground truth, which is how we benchmark how well we do. But they also provide very, very good quality calibration. They have high quality IMU. They have very fast IMU data. So it's sort of like it's a real data set, so it's got noise, but it's a really nice data set where you don't have to worry about calibration and such like. So we're running the algorithm that I'll talk a little bit to you about today on that data set. And these are the state-of-the-art results around the world, right? So at the top here, so this is the room. This is a Vicon, a LiDAR readout of the room, just to give you a bit of a feel of what was flying there. This in the top left is a little quad that they were flying. The data set's about four years old now, so that would be a quad from about 2016 or so. And these numbers are root mean square error. So they're how far away your trajectory is from the ground truth at time t, take that number, square it, integrate over time, and then take the square root of the whole lot. And so if you get a number here of what we've got in that first data set, so these are the data sets that we tested against. So we're on average 7 centimeters away from the true position of the quad doing that, right? And so you can see the sort of the numbers that we're getting. And these are the state-of-the-art, the various state-of-the-art algorithms that are out there doing things in the way we're doing them. So this is using filtering technology, which has the sort of computational load that you can put on these sort of systems. And so just to get a feel for how that looks on the actual thing, if I run this and zoom up to the end and then just pause it for a moment, you can see the blue is the true trajectory and the red is our estimated trajectory. And so you can get a little bit of a feel that, you know, the actual visual inertial algorithm is working really, really well. So what I wanted to do then for the rest of this talk, so I don't want to bore you too much with some of the technical details, but I wanted to try and take a tack through ArduPilot history to explain and give you a perspective on why what we're doing is going to work and why it works as well as it does, and then come back a little bit towards the end and let Pieter talk a little bit about how it actually works. So and what we're doing, present a few of the results flying on a quad last Sunday, which of course we're very proud of. So at the end of the day, the take-home messages of what we're doing is to respect the geometry of the problem and to exploit the symmetry. And so this is something that I've been doing from way back. So those of you that have been with ArduPilot from the start would know that there's this underlying filter that sort of sits there in the attitude estimate and provides sort of a backup basis for attitude, and that's a DCM that came out of work I did way back in 2005. And it provides a little bit of a perspective on the whole perspective that I'm taking in all of this work. So the way to sort of see the difference is to think about how you might filter for attitude. So how do you estimate attitude, right? And so one way of thinking about estimating attitude is to consider the angles, the roll angle, the pitch angle, and the yaw angle. And so everybody thinks in terms of these Euler angles. So it's the way you conceptualize attitude, right? You know what a roll looks like, you know what a pitch looks like. So you can think in that way, right? And so that's sort of the most natural way to conceptualize the attitude of a vehicle, but it's not the most geometric way of understanding a vehicle. And we sort of know that from roll and pitch, right? If you roll 90 degrees and then pitch 90 degrees and then yaw 90 degrees, it's sort of the same as doing them in different orders, and it all gets mixed up, and it doesn't make sense. Roll, pitch, and yaw only makes sense when you're making relatively small rolls, pitches, and yaws, and that's all to do with the fact that it's an incorrect geometric representation of the actual object. So the actual object is a rotation matrix, right? And so the actual object that represents attitude, if you take roll, pitch, and yaw, you can create this 3x3 matrix by taking cosines and sines of the various roll angles. So I think the roll angle here is A, the pitch angle is B, and the yaw angle is C. And you create this horrific big mess of all of those angles, and you get a 3x3 matrix. And if you stop thinking about the roll, pitch, and the yaw, and you just think about that matrix, suddenly things become beautiful, right? So in particular, the angular velocity, so this is the roll, pitch, and yaw angular velocity. So this is the angular velocity around the x-axis, this is the roll, around the x-axis, so that's roll, around the y-axis and around the z-axis. So there's this sort of structure that we can make a 3x3 matrix, and then the actual kinematics of the rotation become this beautiful equation here. So this was some work that we were doing back in 2005, and so we said, okay, well, if that's such a beautiful equation for the kinematics of attitude, why aren't we actually using those kinematics to build the observer? And so we have an IMU measurement, so we can put what we call an internal model, which goes in here. And so that gives the sort of the best estimate of what we expect to happen, and then we add on to that this correction term. So something to basically look at the measurements you've got and make R hat go to R. So that's sort of the idea of the observer that's embedded in the DCM, and indeed embedded in all of the EKFs now. But the really important part, the thing that makes it work really, really well, is this idea of looking at a specific error. And so this is really nice when you look at the matrix structure. So this error E is a matrix. It's a 3x3 matrix. You think about, you don't measure this directly, but you can analyze the problem in this way. So you think about having the true attitude here, which is a 3x3 matrix, and your estimate attitude here. And what you get is this really nice structure whereby the kinematics, so the evolution of the error, no longer depends on your IMU at all, right? So if I take the derivative of this error, I'm going to get sort of R omega in this first bit. And then when I take the derivative of R hat to the -1, I get this minus, I get an omega. I won't go through the maths, that's not necessary. But the real interesting part is the way that you get this beautiful, beautiful set of kinematics out at the end. And so then we did some stuff, and we did the DCM filter, and the multiplicative EKF for attitude is based on this, and that part of the EKF filters that Paul's been doing over the last 10 years or so is also utilizing these ideas really strongly. And it all comes down to respecting the geometry, right? So this really is a case of not using what we conceptualize as a human, roll, pitch, and yaw, not trying to impose that on the way we actually do the algorithms, but instead going back to the mathematics of the algorithm and finding the elegant representation that actually works. So that's actually where the DCM came from. And if you remember back in those days, the DCM was so exciting because at the time, people had been building attitude estimators usually using the Euler angle representations, and they were infernally hard to tune, right? There were I remember there was years and years there, about 5 years, where people just couldn't make attitude run reliably. And then we came up with this trivial filter, which has its problems, mind you, and that's why we don't use it these days. But it's robust. It never breaks, right? And it never breaks because it has this underlying respect for the geometry of the system. All right, so I just wanted to make one comment here in that how you build the error is really important. So this error here is an equally valid error, right? So what you want to do with this error is you want R to equal R hat. And you can see that if R and R hat are the same, then the error is equal to the identity matrix, right? And so that's something nice that we can build a designer on. Okay, and we have the old error here where the star is, the 2 stars on either side, and you can see that this error is R hat to the -1, and this error here is R to the -1 R hat. And interestingly enough, just that little change changes the aerodynamics. So when I take the aerodynamics of this equation, right, I get something which is still not terrible, but it's not as nice, right? Remember in the other aerodynamics, I had cancelled these terms out, right? And so there's this underlying concept, which is that it really matters what error you choose, all right? And so when you tackle these navigation problems, you need to think about what geometry to use and what error to use. And if you get those right, then you start building these very robust, very powerful filters that actually work extremely well in practice. And that's what we're doing. So now I want to take a little moment to talk about inertial navigation systems and what actually is going on in an INS system, right? So the key thing that you're trying to do in an INS system is estimate the position of the vehicle, the velocity of the vehicle, and the attitude. And of course, I'm going to write the attitude as this 3x3 matrix, right, which encodes the roll, pitch, and the yaw. And a few years ago, there was this really cool geometry that came out, which encodes all 3 of those in the one block matrix. And this is the matrix here, this one here, and it's super cool, right? It wasn't me that came up with it, by the way. I actually found the same geometry a few years after it was come up with, but this was developed by a guy called Bonnabel, who's in Umea at the moment, working with his wife there, dodging COVID in France. Anyway, what's so amazing about this is that you can take the INS equations and you can actually write them as a matrix equation. So if you think about the INS equations, right, it's x dot equals v, v dot equals g plus the rotation of the body fixed frame acceleration, right? So this is the acceleration that you measure from your IMU. This is the rotation that then puts that back into the inertial frame rather than the body fixed frame. G is the gravity vector, so it's, the little g 9.8 times the down direction. And so that would be the kinematics of your system, and then you'd have your R dot equals R omega cross. And so normally in INS filters, people write down those 3 sets of equations and start working with those equations. And this matrix allows you to write that out just in one matrix equation, right? You can sort of see it that if I take a derivative of this term here, I'm going to get R times omega, right? I'm going to get the R omega cross term. The x dot here is going to be equal to, well, there's a 0 here, but I'm going to get V times 1. I'm going to get the V coming out of that term, and then RA comes out of that term. I'll let you, if you're interested enough, I'll let you do it afterwards. But the point here is this is like mega cool, right? That equation, admittedly, I'm an academic, right? And I find interesting things amusing and enjoyable, but this is such a beautiful equation that it really is something worth using if you can. So then the INS equations can be written as this really really compact and simple to understand equation, right? Where the U matrix here is going to capture some IMU measurements. So it captures all of the stuff from the IMU, and the V here is going to capture the actual state velocity information that you need, and the gravity information. So the external information and the state information that comes into it. So you get this very beautiful equation here, which we can use to build our observer, right? So again, this is an observer that respects the geometry of the problem, right? So we've got this really cool geometry, and we can do something with it. So again, we can now use this error, which is just beautiful, and we can look at the error kinematics and start asking questions about designing observers. So that's the equation that we get here. Now, this isn't quite as easy to design as the attitude problem, and this is why I actually didn't figure out how to do this back in 2008, because I didn't know how to do it at the time. Sylvain Bonnabel actually developed these equations sort of through the 2010 to 2015 period. And interestingly enough, even though it's not exactly what's going on, it is really closely linked to what is actually going on in the RGPilot EKF3. So this geometry is being exploited in the RGPilot at the moment, not through the route that I've explained it, but through other routes that have got the same approach. So the trick that is used to be able to design decent filters here is to linearize these kinematics. And the neat thing is that because you've got this unified way of understanding the problem, you've got a unified way of putting local coordinates on the problem, okay? And so this is a trick which is to say, okay, I've got this geometric error, which is of a very high quality. And what I'm going to do is I'm going to have a really neat way of putting some coordinates on that respects that geometry. So not just any coordinates, but coordinates that respect the geometry. When you do that, you get, in the linearization, you get this equation. And the point about that is that within those coordinates, that linearization is actually exact. So this approach actually reduces the filtering problem, not to a linear problem, but to something that's as close to linear as you can actually get. It's time varying because the linearization depends on the velocity, right? But it is very, very close to linear. And so because it's very, very close to linear filtering methods work. And that's where the EKF3 is actually, it's working in this sort of space. So given that you have such a nice linearization, then you can throw, and I won't explain standard Kalman, but this is just a Kalman filter for a time-varying linear system. And what you do is you design the innovation using the filter, and then you lift that innovation back to the actual geometry of the main system that you are dealing with. And so the filter that you get is designed based on linear filtering principles, but the actual implementation respects the geometry. And so those filters, that's basically what's going on in the RGPilot, and it works extremely well. So this gets us to where we're going with EquiVIO, right? So in a sense, you can see the progression, right? Back in 2000, 2005, we knew about the set of rotation matrices. It's actually a classical Lie group, which has been known about since the 19th century. But the geometry of it really was worked out in the early 20th century, and people have been using that geometry ever since. So when we did that work, we just had to go and pull that off the shelf. The INS problem, to understand it, really understand it in this geometric way, needs a Lie group that's that SE23 that I'm talking about that's so cool, this guy here. It needs a Lie group that wasn't a classical group. So this is one that Bonnabel came up with back about 8 years ago. And so the recognition that is a Lie group and what it actually does is quite new, and with it you can get this gorgeous interpretation. And in parallel to actually understanding that interpretation, people have gone ahead and got that geometry through anyway, as you know, clever people do, and that's where the multiplicative EKF goes and some of those aspects. but it provides a sort of a coherent way of understanding what goes into making those filters work so well. And now for the Equi-VIO, what we've been doing for the last about 4 years is trying to figure out how to get a geometry that works for visual inertial odometry. And last year we managed to crack that. So we had worked out how to deal with visual geometries a year and a half ago. So that was last year's talk where we were coming from. The problem was that the geometry has to also incorporate the inertial parts. And we managed to crack that mid last year. And so we've just got to the point now where we're able to actually build algorithms based on the principles I've said and see how they work. So the key thing that we're doing here is we've got this new geometry and this new symmetry. So we're going to pose it on the group. We're going to use the symmetry for the error, and the reason it's going to work well is that the linearization that we use then for the filter design is exact. So I've got a slide here which really I don't want to waste your time with, but I guess it's worth just mentioning a couple of things. What actually do you have to do VIO, right? So VIO is all about the inertial state of the robot. So these are the inertial navigation states, right? Rotation, position, and velocity. And then when you use the camera, what you're going to do is you're going to estimate something in the environment. And at the moment, the way we do that is we estimate a series of points. So each PI here is an element of the environment. So it's a point in the environment. And so that's what the algorithm does, right? So and of course, the rate of change of a point, as long as it's attached to the environment, is equal to 0. So what we do is we look in the environment, we find a static point that we can see recognize in the image, we track it over time, and then in our state, we estimate the position of the point. And by estimating all of that together, we can actually see motion of the robot through the space. So the geometry that we use is, the first part is the same SE23 geometry for the inertial states. And then we have to introduce a rather unusual geometry on these points. And it involves a bit of a rotation matrix, which isn't the state of the robot, and a scaling factor. And the reason we've got these two parts of the geometry is that when you have a visual bearing of a point, the symmetries of that bearing, the things that you can do with it symmetrically is you can rotate the point and you can scale the point. But you can't through the view of a camera, because the camera is a bearing. You can't actually do a 3D transformation in a symmetric way. So you have to split the understanding of how you deal with points into rotations and translations for every point. And that's sort of the underlying symmetry that we're talking about. And again, look, I'm happy to talk to people if you're interested. I'm just trying to give a high level view of what's going on. So a really last word to talk about. So, I mean, that's all I want to say about the reasons why things work, but I wanted to take just a moment to talk about what goes wrong. And not what goes wrong in the practical sense, because Pieter will talk about that, but what goes wrong theoretically. And a really important thing goes wrong with visual inertial odometry, and that's that you actually can't tell the difference between the points being in a different place and your robot being in a different place, right? So it's exactly the same thing if I see a whole bunch of points on a sheet on the ground and Andrew Tridgell goes and grabs the sheet and pulls it sideways, and at the same time the robot moves. Everything from the point of view of the robot is the same, right? I have no GPS. So I can't tell the difference between moving the points and moving the position of the robot, right? And the other thing that you can't tell is yaw. So you can't tell if I rotate that sheet, the difference between rotation. So you've actually got yaw, this yaw here and position that are what we call unobservables. So you can't actually observe them from VIO. Now, this is a bit of an issue, right? Because the whole point about VIO is what you want to do is servo control position, right? You want to use it to tell you where you are. And so what we actually end up doing is we estimate as much as we can. So all of this subject to the fact that the position and the yaw can't be estimated. And so one way of thinking about that is that you don't estimate this, but we actually have a slightly cleverer way of just estimating the information we can and then estimating what's left. But it does mean that the algorithm that we have has two parts. One part, which is a filter, and the filter itself has a part of the state that's still unobservable after the filter. And then what we have to do is do a secondary optimization to determine those parts of it. And mathematically, this diagram here sort of represents what's going on, in that there's a part of the state here, which is this flat sort of curvy surface, so the manifold, you might call it, that you can estimate. And there's parts of the state that you can't. And I've got three trajectories here, a red trajectory, sort of dotted yellow, and a dotted green. And from the data, you can't tell those trajectories apart, right? Any one of those trajectories could have caused the data that you see. Okay. However, so what the filter does is it estimates the equivalence class. It estimates the information it can do, and then what we do is we have to have this separate algorithm which rebuilds an estimate of the actual trajectory. So when you see the results that we're getting, we've actually got two things going on. One of them is this filter, which is as robust as the DCM and working as well. And then secondarily, we've got this extra optimization step, which is sort of reconstructing the position and the yaw of the vehicle from an assumption. And the assumption that we use is that the points in the environment aren't moving. So if you do have a particularly annoyed Andrew Tridgell there pulling the sheet sideways while we're trying to fly, then we've assumed that the ground is stationary, and so we'll simply make a mistake about where we are. So don't use a VIO algorithm over the top of a train or something like that that's moving, because it's just breaking the underlying assumption of what's going on in the world. So I had a little bit of a chat about why equivariant VIO work, and I appreciate you your patience in listening to me, because I know I tend to be a bit academic. What we want to do in the group is we want to take this filter, which we believe is the best in the world, and we want to take a step from running it on these academic examples and proving that it works academically, which we can do now, and actually roll it out as something that everyone can use in ArduPilot. And so what we're running into is the reality of all of the issues that come up about making a piece of code that the mathematics works really well, but now actually making it work well in practice. And that's where we're really coming to the ArduPilot community. This next year, we've actually got something now that we can start testing. And what Peter's going to talk about now is a whole bunch of stuff around, what we've been running into and how we've been solving the problems. And then we're looking for feedback about, what do we need to do to really make this become something that everyone can use. So I'll end there. Peter, are you around?
Yep.
Right, so I'll press stop share. Did I stop sharing there?
I think so.
Great. Okay, then, Peter.
I'll start on mine. Yeah, so as Rob mentioned, I'll talk a bit more about the practical obstacles we came across in the last 2 weeks trying to take this algorithm from something that works great in theory and works pretty good on nice academic data sets and needs to work also now on real ArduPilot data. Right? So there are a lot of things to consider, and I'll give a shout out to Michelle, who did quite a bit of this work last year in her honours thesis. So questions around, okay, the board that you're using to do your ArduPilot stuff probably isn't strong enough to run VIO. You might want to have a companion computer. Then you, of course, need a camera to be able to do anything visual. And what camera should you use? What properties should it have? And finally, one of the issues that we came across, particularly in the last 2 weeks, was the issue of the different time domains between the MAV, which is sharing the Imu data with your companion computer, and the time on your companion computer. but I'll talk to each of these points in turn. So first, our hardware. We're flying a custom quad rotor. So Rob's here. He's got the quad in there. Nope.
That's good enough. Ah, it's mine.
I don't know why you're...
Don't worry, I can see
okay.
enough. Yeah.
But yeah, so we have the quad. There it is in the picture, right? We have a companion computer. We used a Raspberry Pi 4. And we also have a ELP global shutter camera. If anyone's really interested, I can give you the model number later. Okay, so choosing a camera, one of the things we know is there are two things we know are important for visual odometry, visual inertial odometry type algorithms. The first is a global shutter. So that means that every pixel is fired at the same instant. And what this prevents in particular is sort of tearing effects. When you have fast motions and you use a classic rolling shutter, this half of your image is a little bit in the past relative to this half of your image, which is no good when you're trying to do an algorithm that assumes everything's happening at the same time. The other thing is that we want a wide field of view. So we want to be able to get a lot of information around the robot, and this really helps with motion estimation. So I mean, there's a reason that our human eyes can see something ridiculous like 130, 140 degrees, right? And it's because it really helps us, estimate our own motion. And then what I'm showing you in the videos is we had to try and tune the exposure of the camera ourselves. And this can be sort of challenging. So, however, there are existing computer vision techniques, in particular histogram normalization, that can basically get around this. So you can, in the top image, there was a bit of flashing, lighter and darker of, there you go. While the bottom image remains relatively steady. So the bottom video is processed from the top video. Okay.
Isbro has a question about the isolation of the camera.
Ah, sorry, I don't have my...
Sorry, just I noticed that the camera appears to be isolated separately to the frame in Autopilot. Was that angular changes in angular alignment cause you any issues?
I'm not sure what you mean by isolated separately.
Well, I saw that the camera was sitting on a little test fixture, and it's on with the rubber mounts to the airframe, but the autopilot's on the top of the airframe. So in other words, you've got an angular alignment difference between, it could potentially change alignment between the camera and the autopilot where the IMU sits.
Yes, and this is a very important point. I'll talk more about it on slide 9, I think.
Okay.
But in general, right, you can never put your camera and IMU in exactly the same spot with exactly the same axis alignment. And the calibration of the relative rotation and translation between them is a really important part of making visual inertial odometry algorithms work well. So for those of you who've played with the RealSense T265, does visual inertial odometry on board, they have an IMU inside their camera, so they know exactly how to align their two visual cameras with their IMU. But of course, we want to make something that's a bit more accessible to everyone in the community, and everyone's going to put their camera in a slightly different spot. So yeah, I will talk about calibration. Okay, but for now, I wanted to mention the time domain differences. So the first thing we know is that, of course, both times are measured by a different, on a different computer, right? The MAV will give me a time stamp, which is some microseconds since boot. And then I have to translate that into a time on the Raspberry Pi. So that time lag is an issue, and we need to try and compensate for it. But aside from that, what we found is that there's also a jitter in the time delay. So this is just because the IMU messages coming from the from ArduPilot through to the Raspberry Pi, you know, sometimes the message comes very quickly, sometimes not as fast. And so what I did is I left the quad sitting there for an hour, recorded messages over the whole time on the Pi, and compared, okay, well, what's the, so setting the first timestamp for both the MAV and the Raspberry Pi to 0, what's the difference between all the relative timestamps? And so what you see is there's a distribution, and it's roughly plus or minus 2 or 3 milliseconds with a few outliers. That's going on. Now, Tridge and I have been talking. He has a really nice algorithm to try and compensate for this jitter. And we're very keen to work on that and implement that in the future. The other thing that we saw, which was interesting, was the slow drift of the relative time difference. So for the time scale on which we're flying of a few minutes, this doesn't matter that much. We're talking about 5 milliseconds over an hour of on time. That's this, this slope in the bottom graph. But of course, if you wanted to do visual inertial odometry for 10 hours or a whole day or something, you would have to realize that, you know, by 10 hours, you're going to have a 50 millisecond time shift purely from the difference in time scale between the Raspberry Pi and the MAV. So this is another practical problem that you just don't have to think about in the academic data sets. In the academic data sets, you get this, you get an IMU, it has a timestamp, you have images which have a timestamp, and they're exact. So how do you calibrate all these systems? So we have effectively 3 things we need to work out. We need to work out the Imu noise characteristics. And we're not very keen on trusting the data sheets in this case. We also need to work out the camera intrinsic parameters. So this is things like the focal length, the image center, and things like that. And the last thing, perhaps, well, one of the most important ones is working out that alignment between the camera and the IMU. So these things, as I emphasize on the slide, should all be straightforward, but they tend not to be. Well, I mean, the IMU noise and bias are. So we model the IMU as having a Gaussian white noise and a slowly time varying bias. You can find both of these just by doing an Allen deviation plot. And so these are, well, that's what's shown on the right. And that gives you the noise and bias parameters. So with our quad, we found the accelerometer is a bit noisier than the gyroscope. But yeah, neither of them are particularly terrible. Okay, but knowing these noise parameters is really important to identifying that alignment between the camera and the IMU. So how do you calibrate a camera? Well, you choose a camera model, and then you use one of the standard calibration algorithms to find your camera parameters. So you can see in the top, we have the uncalibrated video, and what should be straight lines look like curves. So you can see the edge of the desk is really bow-shaped, whereas in the bottom image, all the straight lines are straightened out. So this is a rectified video. Which is important for making sure that the assumptions we make about the geometry of what the camera sees are actually satisfied. in our algorithm. So one of the problems is that, so the pinhole camera model, which is what we decided to use in this case, works very well for the center of the image and not so well for the outside. So you can notice as well that the bottom image actually cuts off a lot of the information around the edge of the top. You can see it cuts off way lower than the top image. So there are other camera models which can do better, but they don't have quite the same number of calibration tools immediately available. And so that's why we've gone with Pinhole for now. But investigating fisheye camera model or a double sphere camera model, which is a nice piece of work from a few years ago, is one of the next steps as well. Okay, but this calibration really is sufficient for at least the center of the image, and we can always crop out the outsides, even if that does reduce the, reduce our ability to do the motion estimation perfectly. Okay, now in terms of Imu and camera offset, this is where this is typically done with a big optimization algorithm. And so you take your Imu data, you know that the offset, you assume that the offset between the Imu and camera is constant, and then you effectively try and solve for the trajectory of the camera and the offset from camera to Imu. It can be a very sensitive problem. It was solved to some degree a few years ago in the academic community, and they released a really nice software package called Calibrate, which is still on GitHub, and it still works for Ubuntu 14 and Ubuntu 16, but has not been updated. So it's very hard to get it working now. It relies on a lot of out-of-date packages, and it's not really set up to be able to handle losing particular packages. For example, Sean, a guy I was working with, tried to use it to calibrate our Imu and camera, but the system failed because it couldn't find a graphing package for displaying the results. So we solved the problem a bit differently. We estimated it roughly, effectively by hand, by saying, okay, well, we know where the Imu frame is. We know roughly where the camera frame is. So now we put in some parameters into our configuration file, and then we solve it more accurately using our filter tuning. And that's the next thing I wanted to talk about. So on the right, I've got a picture from one of the configuration files for the VIO system. And as you can see, there are a lot of parameters. And unfortunately, the performance of the algorithm is quite dependent on choosing sensible parameters. So what we did so first we tuned it manually by hand by choosing sensible values for each of these things. And that's not too hard to do, but the end result of the filtering isn't very good. But what we realized is the fastest way to tune it is just to take a flight, look at the GPS data and say, well, we want to match the GPS data as best as possible, and then simply run an optimization scheme overnight that changes the tuning parameters, runs our algorithm, compares it against the GPS, and slowly but surely finds optimal tuning parameters for our situation. And so this, if you have a reasonably long flight, your quad will or your UAV will see a bunch of different situations, and you'll be able to let it tune itself on your computer. And then you'll have good parameters to fly the next day. So that's what we did. And we set ourselves a goal to do some skywriting and write EQF and underline it. And then we wanted our EQF algorithm to estimate that trajectory really well. So as I mentioned, the real data is more challenging than the academic data sets. And that's why we had to do quite a bit of work to get to this point. But we're very keen to try and write some notes on our experiences and make it a bit easier for other people who want to get into visual inertial odometry and using this sort of algorithm for state estimation. So the videos on the next slide are our results. They're not time aligned, but they show off what's going on. So in the top left, we have the actual view from the quad rotor. In the it's left the audio in. Has it?
I'm happy to have it fly slower.
Oh. Oh dear, it's not. Okay. The top left is the view from the quad. On the right, we have the trajectory. So the the GPS trajectory compared with our estimated trajectory.
I'm happy to have it fly slower.
I'm sorry, it's I thought I'd cut out the audio from my recording walking videoing the drone on the ground.
Coming up on the end of the E.
Don't worry, Peter.
Yeah, I'll just go on.
My commentary,
Anyway,
I was on the ground station and I was explaining to Peter where we were in the skywriting as he was the different parts of the lettering.
Great. I really thought I cut out the sound. Anyway, the three different views. So you can see the trajectories line up very nicely on the EQF. We can underline it at the end. And one of the things I'll point out on the next slide as well is the... I'm going to go to the next slide. There we are. Okay, so apologies for the talking over it. That was to show you what was going on, right? So we flew for over 200 meters, and in the end, we achieved what we call root mean square error of 1.75 meters. So we, as academics, are very happy with that. The other thing that's worth pointing out, that's interesting, that's missing the underline.
The truth data isn't necessarily truth. We weren't using an RTK GPS, which we should have done, because there could be some error. It was just using an ordinary M8 GPS. And so it would be perfectly believable, in fact, expected that there be more than a meter of error in that position from, it was really the EKF3 solution it was using. There could easily be more than a meter. There probably is more than a meter of error in that.
Yeah, so, and as you can somewhat see from the alignment, I mean, there is some error in the X and Y positioning, but there's substantially more error in the altitude as well. But yeah, so these are the results of the filter. And we're keen to, well, there's plenty more work to do to improve these results. I think we can still do better, but it's a good indication of where we're going. So in terms of future work with the practical implementation, I'm very keen to try and remove the jitter from the timing. So that should help improve the using the Imu signal. There are lots of different camera models, and I expect that people in the community will want to use lots of different cameras. So I also don't want to set it up to only work with fisheye or only work with Pinhole or anything like that. We want to be able to support a variety of different camera models. Now, another important thing is, of course, it's all good and well that we can estimate the position and attitude of our quad, but we want to give that back to ArduPilot so that ArduPilot can actually use that in lieu of a GPS signal. Then, as I mentioned, the calibration is quite challenging. Well, the camera intrinsics are easy. The Imu Noise is easy. but the measurement of the Imu to camera transformation is difficult. It really is. It's easy to get wrong if you do it by hand, and a small error in the attitude alignment especially makes a huge difference to the performance of the filter. So if I change the angle by a few degrees, that can reduce the increase the error in the filter by a meter, for example. Then another thing we were interested in doing is looking at fusion of other non-GPS sensors. So in the academic community, people are very focused on just the IMU and just the camera, sometimes two cameras, if they want to go for stereo. But in practice, even if you are GPS denied, you might have your barometer, you might have a compass, you might have a rangefinder, something like that. So there are a few other sensors that we really could try and integrate as well. And finally, again, the academic community runs these algorithms on something like the Europe data set, and there are 10 sequences in that data set of about 2 or 3 minutes of flight each. And that's of course pretty much no time at all compared to how much flight is being done with ArduPilot every day. So if we want to roll out this VIO, I expect there will be lots and lots and lots of testing for all different setups. And I'm very excited about that as well. I think that'll be a great opportunity to really develop this algorithm into a robust solution that works for everyone. Okay, and finally, special thanks. Tridge helped me fly everything last Sunday, so greatly appreciated. As well as all the discussions about timing jitter were really interesting. Thanks a lot, Tridge. Michelle actually sort of built that quad, or at least set up the companion computer and the camera, and a lot of the software interfacing between ArduPilot and the Raspberry Pi last year. I don't know if we would have managed to get our demo ready in time without the groundwork that she'd done. And finally, Sean is another student here who's been working with me on this. He's not here today, but yeah, well, he helped get it all running. So thanks a lot, and let me know if there are any questions.
Well, congrats on getting that working. That's really impressive.
Thank you.
Yeah, really nice piece of work. I think we should fly again with an RTK, and what I think we should actually do is have multiple EKF3 lanes. One of the lanes set up to use the RTK GPS, which means the EKF solution could be considered truth. And then a second lane set up to use the cheap, affordable M8 GPS, which means, and then we have the VIO solution, and that gives us in one flight truth plus how well it can estimate with a commodity GPS and how well it can estimate with a commodity camera. And that actually gives us a real comparison for, is this in the same ballpark, particularly over an extended flight? If you could do like a 20-minute, half-hour type flight, just by throwing more battery. And we do have a vehicle out there that could carry a lot of battery. I'm thinking the Lift Octo that we have from Canberra UAV. That's the one we're doing the water gliders off. It could actually fly for quite an extended period of time. And that could be like a definitive data set that includes essentially truth data like you would get in a Vicon, but out in the real world with comparison to what an EKF with a commodity GPS can get.
So this is another interesting point about what sets these geometric filters apart a little bit. And Rob briefly mentioned this, is that the fiber structure Rob was talking about, where we have a smooth base space and then this secondary optimization. It's a really important part of what makes our algorithm work, and in principle is what is really important to our algorithm being quite robust relative to the existing works. So in the existing works, you don't separate this structure, and you end up with unbounded growth of uncertainty, which, in principle, it might not kill your filter in 5 minutes. It might not kill it in 15 minutes, but eventually your filter will stop working. The corrections it'll make to itself will be too extreme. Whereas what we do by using the fiber structure is our uncertainty on that fiber structure always remains bounded. And then the secondary optimization doesn't have the boundedness problem. And so I think gathering a long-term data set, a really sort of 30-minute flight or something like this with good GPS RTK truth data would be a super interesting experiment, and maybe a real contribution to the academic community as well.
It should be super easy for us to do. Now we've got this set up. Next few weeks we could go out and do that, gather that data set if you've got the time. It'd be fantastic to get it, I think, and see how well it does. I'm interested in the handling of moving features. So, out at Spring Valley, for example, the bulls and the horses are probably wonderful features, right? But it's inconvenient to tie them down because they don't really like it if you go and chain them down during your flights. So they do actually walk around the field, but I imagine that the visual odometry thing would look at a bull and think, that's a great feature, nice little angles and things. There's the horns I can lock onto, that horse over there, that's a nice feature.
For sure.
How big a problem is that? I mean, could we eventually use this, in a farm environment where you have cattle and sheep and those sort of things?
Does it run a median? I mean, if you've got a lot of points there. So if some of them are moving around, if there's some form of a median filter.
Yeah. So let me jump in. One of the things in the state-of-the-art visual inertial odometry and VSLAM that goes on in what they often talk about a front end and a back end, and in the front end they identify points and they track points, and then there's this big chunk of code which we don't want to write which basically goes through all the points and says, oh, this is attached to a cow, it's moving, throw it out, don't use it, this is attached to a car, or this is moving, or this is unreliable. And so it's and then it also does the data association. So it says this point is the same as that point was in the last scene. And it's a really big chunk of code in a lot of these algorithms. And it does improve results, but in those algorithms, it's really critical for robustness that if you don't do that, you end up with instability. And we actually think that because we've done the geometry properly, we can still be robust, but just have a slightly less reliable solution. So it's one of those things where we're writing a piece of code that we want to work for everyone, right? And so what we don't want to go down a rabbit hole where you end up with a big complex piece of, logic that's trying to do something too difficult, because it's just going to break, And so we're actually thinking about things like actually, instead of using points, just expanding that out into big chunks of space. So particularly for flying vehicles, where a lot of the time you take off, and then while you're down close to the ground, points are great, right? But once you take off and you're 30 meters up, a lot of the ground just looks like a flat sheet, right? And so if you can find a flat sheet and just match bits of flat sheet, that's going to be much more reliable, and that's going to take out some of these things. That's how we're thinking.
I think that's a really good point, Rob, because you're much better off having a performance that degrades more gradually and is less brittle. And the problem I've seen with the algorithms you've mentioned is that they tune them up for really nice performance on their specific data sets. And then when the algorithm fails, it fails spectacularly.
Yeah. Completely blows away,
Yeah. So
talking about other sensors incorporating, is it worth incorporating an optical flow sensor to help with the rejection of some features because you have a basic velocity over the ground. Does that make sense?
So at the moment, one of the things to point out is that in the video we took on last Sunday, we actually have a moving object, namely the leg of the quadrotor is visible in the camera.
Yeah.
Right? And that isn't static in the world, right? It's moving along with us. And my algorithm's very happy to pick up some features. It's a black leg and a lighter background, so it's great. The simple solution is just a straightforward outlier rejection, which says, I have some estimate of how I have moved since the last frame. And if the points are really not where I expect them to be, then it's probably not satisfying the static world assumption. So that's how we've done it at the moment. There are more sophisticated solutions that might work a little bit better, but I think that's the most practical thing to do. When you're talking about flying over a huge group of cattle, it depends, right? If 80% of your screen is taken up by moving objects, that might be very challenging. But as long as, as long as you've got mostly static environment, it should be okay. In terms of adding an optic flow sensor, I think it would suffer from pretty much the same problem.
Different scales, I guess. A thing I thought of is currently you're using the raw IMU Mavlink message, right, coming in, which means part of the problem with that is that's been filtered quite aggressively by ArduPilot, and it's filtered in a way that the user controls to change the filtering to suit the, their tuning of it for attitude control. It might be worth instead to be shipping across a delta angle and delta velocity, which is what the ArduPilot EKF infrastructure uses. And that would mean it wouldn't suffer from that problem of user configurable filter for, the wrong task. Would that make sense?
Yeah, so I mean, intuitively, you always want to filter on the on sort of the rawest signals available. So, but we can have a longer discussion about which signal exactly do we take from the IMU.
Yeah, it's actually an interesting point in that the whole thinking that's gone into our algorithm up to date has grown out of the systems and control community. It's all based on continuous time analysis, right? But the reality is that everything in a computer is in discrete time, right? It's all quantized and discrete. And there is a theory there to do discrete time versions of this, to do forward integration exactly, so you get delta angles rather than actual IMUs and all of that. So, I mean, being who I am, of course, what I want to do is do the proper mathematics of it and do it properly. But I'm also aware that maybe we should just like jump in and do a few hacks and get something working. Probably in terms of resources in our research group, it's going to take us a year or so to get around to the actually solving the discrete time problem properly. And maybe we should do something in the meantime. I mean, this is one of those things, right? I've got different agendas. One of the agendas absolutely I want to engage in over the next year is making this work for ArduPilot and start to roll it out, because I think the algorithm's there now. But I've also got my eye on the academic sort of markers for the future too.
Yep. I'm really looking forward to us closing the loop. I'm slightly concerned about the delay, because there's going to be a delay. The IMU data coming out of ArduPilot going across the link to the Raspberry Pi, the VIO processing on the Pi, bringing it back, and then ultimately it's going to be fused in via our VIO methods, via our sort of external navigation, data, velocity, position, etc., into Paul's EKF, and the total delta of that time, I don't yet know how many milliseconds that's going to be. The discussion I had with you last weekend, Pieter, was quite encouraging. You thought it was down in the milliseconds range, not the hundreds of milliseconds.
Bridge, I was given that some thought, and from the, I mean, there's a two-way perspective. I mean, the VIO can afford to run it, provided it's able to buffer some of the data so we can time align the inertial data coming across. I assume that it's doing some time alignment internally. So its calculation is on a delayed horizon, and then we take that back to the EKF, and the EKF is set up to be able to handle something back in, swallow something back in on a delayed horizon. So as long as we know, as long as we've got a common definition of time and time stamping, it's all very doable.
Yeah.
How accurately can we get that? Can we get it to a millisecond?
So, Paul, in principle, if you start messing with the hardware and go into like you have direct MIPI access to the camera, you've got common clock across camera, sensor, image processing CPU, and potentially even the autopilot side of things as well, you can get that delay down probably sub-microsecond without substantial amounts of difficulty. Now, that's going to say that you're going to have to probably leave the Pi and go to something like IMX6 for your processing. You're probably going to have to, you might have to go to a Sony sensor, for example, just because there's drivers for that. And then in terms of synchronizing the clocks between all that, there has to be some sort of common clock structure, whether that's going to be a pulse per second and everything phase lock loops off that from GPS, or whether or not you're distributing a 10 megahertz or 25 megahertz base clock for everything, and then doing all of your clock magic from there.
I think we can use the jitter correction and then have a base time. So I think it's quite doable. And I'd like to stick to the commodity hardware for the moment and demonstrate it on hardware that is easily accessible within a modest budget for our community. And it'd be great to have a high-end version of it as well, right? To demonstrate on a high-end one what can be achieved if you can, buy great hardware. But what's so attractive about this is, Raspberry Pi 4 plus, I gave a link in the chat to the particular camera. It's just a camera I found on eBay that is loaded on this copter, and it's a $70 camera. 70 Australian dollar camera, so it's toy money, and that plus a Raspberry Pi 4, that's incredibly affordable, and we really want eventually like a wiki page on you go and buy this camera and you get this Raspberry Pi, you connect it in this way, follow these instructions, and you've got a great VIO system. And that it's getting to that first stage and getting it replicated out so that members of our community can actually achieve this themselves, that we focus on that, I think, initially. And as well as, of course, generating the data for the academic stuff for Rob and Peter's papers, where we want some truth data and RTK and that sort of thing. But making it readily accessible to anyone who's got the room to have this little camera and a Raspberry Pi is just so attractive.
I would love to try something like this on my quad plane setup with the VTOL.
Fixed wing with the higher velocities on fixed wing will be interesting. I'd love to fit it to a small fixed wing, which will allow us to get much longer flights. And like hour or so sort of flights. It's just a matter of how well it handles like the turbulence and the high, velocity. Because it's further off the ground, you don't tend to fly really low with a fixed wing. I presume that it's really the flow rate that matters for this algorithm as opposed to the actual absolute velocity. Would that be right, Peter?
The tracking is the issue, and the worst thing you can do is a very fast attitude change.
Right.
So if you do a very fast roll on a fixed wing, so the number of degrees per second that you've just put into your camera, of course, is pretty high. And if your camera frame rate is only 20 or 30, then frames a second, right? You might get hundreds of pixels of displacement on your image.
We do have a method for the optical flow. Paul added in a method for where the EKF actually tells the navigation code, don't fly above this speed because I won't be able to track.
Oh, okay.
Yes. In fact, I found I had to do that, not only putting in limitations in terms of speed to respect optical flow limits, but also and height limits. But there was also code put in there which we wind down the gains on the position controller to start getting the feedback that you get back, because you can end up with an attitude rate causing a slight perturbation in the state estimates, which feeds back to the position controller, and you end up with a loop.
So one of the outputs of your filter should be, you know, what the navigation limits are, and then we feed that in to ensure that we don't violate them, so that you don't lose track. And that's already in place for Copter. It's not there for plane at the moment. The fixed wing code doesn't honor any of that stuff. We just ignore it. And it's partly a problem because, you know, that code might say, oh, you can't fly faster than 5 meters a second. And the plane will go, well, in that case, I'm not flying anymore. You know, I'm stalling. So, you know, there has to be, we can certainly do roll and pitch rates though, you know, as long as we don't violate our geofences because we can't turn fast enough. But yeah.
Yeah, I mean, one of the things I'm keen to do with it is I was looking at Randy's talk from the other day and the switching and everything. So one of the things we can do is we can absorb the GPS as well, and we can actually we can lock our filter to the GPS, so we can use that as an innovation while we're running. And then if the GPS switches off, we're already synced to it, right? There's no need to resync, right? So because we absorb the IMU anyway, we can just absorb the other stuff from the RGPilot, and then switching back. If the GPS switches back on, you need to think about well then we'll have our estimate. I mean, what the filter does then, I guess the EKF could do the same thing, right? Absorb us and then phase lock that. You know, it just take a little bit longer to respec the GPS again.
The other thing to think about is the definition of yaw angle in the frame of reference, because if we're just using the VIO to fly the vehicle and we're not using GPS, then it doesn't matter. I mean, the yaw, the definition of yaw with respect to, you know, what is your world frame? Where does it align with respect to true north? It doesn't matter. As soon as we start fusing in at the EKF level for the main navigation filter, start fusing in world frame measurement, then that your alignment between the two frames matters.
Yeah, but I can pull a we can pull the state from the EKF, right, and just put an innovation on that state into our filter and at a low gain, a really low gain, so it doesn't really disturb the filter, but it just locks our filter onto the, you know, basically onto the base reference of the EKF.
Oh,
so
okay.
That would be what we should do, is we just get our filter, because our filter is basically floating in space, right? So the VIO, you can rotate it and translate it any way you want without actually changing the underlying filter. That all happens in the fiber.
I like that idea. That sounds good. It's going to make things simpler. And I guess the only thing that's shared between us is the fact that we both agree where gravity is.
So we can't lie about gravity, and you can't lie about acceleration. But you can lie about position. You can lie about yaw.
In fact, you don't. You know, if your system doesn't actually need the GPS data for some reason, I mean, obviously, you know, in this test, you were definitely, you know, looking at the GPS so you could compare, you know, versus reality. But, you know, from the RGPilot point of view, you know, just like the T265 has no idea about the GPS, of course. And so we had to deal with that in the RGPilot side. So, we, you know, like I said in my talk, we have a rotation, we have an offset that we can handle on the RGPilot side if that's necessary.
Yeah, but it makes sense because basically all of this stuff just goes into the fiber adjustment that we're doing. So if the filter doesn't change at all for us, and then we can just use the GPS and just make sure that where we are on the fiber is locked onto the EKF, right? And then if we lose that, that's fine. You know, we're already there. Yeah.
Really cool.
Absolutely fantastic. It's really exciting. It's great to see the progress on this, and Peter's been working very hard in the last week. There's been a lot of progress. I'll have to ask you later, Peter, you know, how did you solve that Z problem that I saw during the week?
I'll take responsibility for the Z problem. Pieter just fixed my mistake.
Okay. Confession time.
I thought of a really clever idea, and it was shit.
Right. Okay. Well, I'll love to hear the story on that later.
Absolutely.
All right. Well, this has been absolutely fantastic. I love that talk, and really great to see the progress. I'm looking forward to doing a lot more flights with you guys and closing the loop.
Sounds great.
Because that's the next big milestone, is to close the loop. So it's actually flying under VIO control, and it takes off and lands in the same position and goes out and does a tour around Spring Valley and comes back and lands in the same position. And there will be a huge cheer when we get to that point. So fantastic.
Really great. I just also want to add that I think, if we do what, Trish was describing, set up a wiki page and tell people, how to set it up and where the code is, and, maybe make an AP sync image or something that helps them to get started quickly. I'm sure there's going to be a rush actually of people to give it a try, whether, that's good and bad, because then you get all these questions and stuff, maybe we could help handle some of those questions and stuff, but I'm sure you get a lot of interest because we have a very active, vision projects channel in RGPilot, and there's people trying all kinds of things, so, I think if we have a system which works, even if it's not like perfect, day one, you get a lot of interest and people, trying it out and uncovering, where it works and where it doesn't work. I think it'd be really, really exciting for everybody.
Then we should have a corpus of data that we publish that other researchers can use. So this, we really should publish it with a set of vehicles, not just one vehicle, but like a dozen different vehicles in different conditions, preferably with truth data with RTK, and that this can be used as a basis for developing these algorithms and improving them over time. So we have to make sure that the logging and the data capture that we have built into this process is sufficient that we can then use that data and bring it in as part of a corpus for the research community.
I mean, and I think if we had the setup easy for the community, of course, included in that, and maybe this is what you're just saying, but a bunch of other researchers, our community has all kinds of people. It has professionals, it has DIYers, but it also has significant research group from all over the world and stuff. And those guys, I suspect most of them, don't want to, they want to get to the core algorithms. They want to get to the hard part first, and this might help them get there faster. If we have proper instructions and stuff. Really, really exciting stuff. I'll do my part.
Yeah. I mean, the place where we've published some papers, so we're happy to have all this go public now. The spot which I think we need to knock over in the next few months to make this really work well is all of these sort of underlying issues, like how do you do calibration? How do we port the OpenCV? How do we get Calibre so it works, for everyone, rather than 4 days of installing old versions of libraries? How do we port how do we port the OpenCV for different camera models, the calibrations, all of those things, right? We need sort of basically to bring all of that together and make it all work pretty seamlessly. And then, the goal here is that anybody can just like put a Raspberry Pi on, put a camera on pretty simply and get data and make something work, right? And whereas if you can't do the calibration well, you just can't turn the thing on, right? So we've got to hit that. Then the algorithm's pretty robust. Then we should have something that we can start then building on.
Brilliant.
Good.
All right.
Thanks.
Also probably you'd have to integrate it with GPS failover, like what Randy was doing, right? Because one thing I was wondering is, how does the algorithm degrade with the number of features? In other words, as the number of features go down, is it more or less linear, the degradation? Let's say I'm on I'm flying somewhere with a quad, not too high, and next thing I know, I am flying over a patch of total green, 0 feature. What happens then? You would, does it just try and stay in place, or does it completely lose its bearings, or
it doesn't break immediately, right? because you've got the IMU, so you would essentially continue flying on IMU. If you have 0 features, things are going to fall apart reasonably quickly. I mean, your forward integrating IMUs isn't a particularly good idea ever. So the roughly the degradation is going to be with the square root of the number of features. So, you know, if you go from 20 to 10 features, it's a square root. Well, 25 to 16 features. There you go. You'll drop by 80%, right? Your accuracy will drop by 20%, right? So usually we run around about 20 to 30 features. That's what runs. Once you get down under 9 features, yeah, you're about half. Yeah, you're starting to lose accuracy, right? But there's very few situations where you can't see nine points that are reasonably stationary.
Because it's a very wide field of view camera.
Yeah.
Right, but let's say it may seem like a corner case, but water. I mean, that's going to do it, right? I mean, when you got a lake in your mission, your history. Technically, well, there may be a few boats, I guess.
Yeah, well,
you get my point.
I'm interested. Yeah, I'm interested to see what we can do over water. I'm super keen to get some data and have a look, right? I mean, if there are ripples and they're not moving too fast and they're all moving in the same direction, you'll be able to pick up the ripples, and then what will happen is, what will happen is the whole world will be moving with the ripples, right? So,
something.
And if there is nothing in a way, I mean, it's not a total failure because a human being wouldn't be in the same situation, right? I mean, if you have 0 feature, and that's it, you just can't go on anymore.
Something it's worth mentioning, and it didn't come out in the talk from yesterday, that with this drag fusion in the EKF, you can actually turn that on, and actually, if that's running all the time and you build up a wind drift, then if you lose your GPS, you can actually fall back to almost like a wind relative navigation with a quadcopter. Now it's a bit drifty, and it tends to but it will constrain your velocity area to about 2, maybe 3 meters per second. So it'll stop that accelerating flyway and extend the amount of time that we can go.
Yeah. Good point.
That's exactly what we should do. That's great.
So, so I saw there's another question in the chat about fog. In general, right? If you don't have visual information, you cannot correct your IMU drift. The same problem happens if you fly very, very high and far away from objects. You know, at that point, a meter of motion will hardly appear in your visual information, and so that also is just impossible to correct for.
Yeah, the origin of this question is there's a couple spots within short driving distances of where I live that have fog that will hug the ground. So for example, if you're on the highway, you'll be driving, you'll come down into a canyon and boom, visibility goes from miles to 0 in 2 seconds.
Yeah. So it depends, right? If you're flying inside the fog and you can't see anything, then too bad. If you're flying above fog, as long as there are things like trees sticking out, you should still be able to run on those.
Cool.
All right. So that absolutely brilliant, and greatly appreciated. So for those of you unmuted, I think a round of applause for Rob and Peter.
Thank you.
Really nice. Fantastic. Really good work. So we're now moving on to the next talk. So we have Michelle. I'll just switch the recording just